In today's video, we are going to be taking a look at Avogadro's law or Avogadro's hypothesis that looks at the relationship between volume and moles and the number of molecules present. Then we will also be taking a look at the main calculation that we have for this unit, PV equals nRT. So that is on our reference tables. You'll want your reference tables and your calculators. So go to page 2 of your notes. The other day we covered some of the basics in gas laws, and hopefully you remember those things from Regents, and if not, then do a little bit of review to refresh your memory. Okay, so first thing we got today is Avogadro's hypothesis, and what that says is equal volumes of gases, as long as they are at the same temperature and pressure, they will contain the same number of molecules and the same number of moles. So hopefully you remember doing this question in Regents, where it was something like 5 liters of helium gas at STP would have the same number of molecules as, and the key was that you had to pick something else with the same volume as long as they were at the same temperature and pressure. Now, the reason why is because if we were going to do our full mole calculation, we would do 5 liters, put that over 1. If we were at STP, we would do 1 mole of any gas will occupy 22.4 liters. All right, so that would get us to moles. And then from moles, we know that we can turn that into molecules. So if we start with the same volume, we're going to end with the same number of moles, same number of molecules. Another application of this is that if the same volumes are giving us the same number of moles, they're going to have a directly proportional relationship. So if you double the moles, you would also double the volume. And that makes sense if we think about filling up a balloon. When you are filling up a balloon, let's say you're blowing it up, you are putting carbon dioxide molecules in there. The more carbon dioxide molecules you put in the balloon, the larger the balloon gets. And it would obviously work the same way if we were filling it up with helium. You are literally putting molecules into the balloon, and that is why the volume of the balloon is expanding. So this graphic is just showing us we've got some helium, some nitrogen, some methane gas. We're at 1 atmosphere and 0 degrees Celsius. And we have 22.4 liters of each gas. So since we have 22.4 liters of each gas and we are at STP, we would have a mole of each gas, so they have the same number of molecules, but they do not have the same mass, because if we have a mole of helium, it would be 4 grams, a mole of nitrogen, it would be 28 grams, and a mole of methane, that would be 16 grams. So they have the same volumes, they have the same moles, same number of molecules, but they do have different masses. They also would have different densities too. All right, you guys don't have this example problem in your notes, but we can just take a quick look at it. So we have 4 different flasks here, and they all have different gases. We've got helium, neon, argon, krypton in there. All 4 of our flasks are at the same temperature, same pressure, and have the same volume. So question 1 asks us, which flask contains the most molecules, and explain why. Hopefully, you said that they would all have the same number of molecules. And that's because they're all the same volume, same pressure, same temperature, so they have the same number of moles, therefore same number of molecules. Question number 2 asks us, which one has the most mass? So take a second and come up with an answer for that. All right, hopefully you said that krypton would have the largest mass since they all have the same number of moles. Whichever one has the highest gram formula mass would be the most massive, and that's going to be Kr. All right, so this is really our big idea for this unit. In Regents, we used the formula P1 V1 over T1 equals P2 V2 over T2. And that was useful, but the really only thing that we can do with that formula is we take a sample at certain conditions, we change one or two of the conditions, and then we see how that impacts the other. So really it's just one sample, and you might heat it up and see what that does to the pressure and the volume. This formula, on the other hand, is really going to be more useful because in this formula, since it's got moles in it, N is moles, we can now relate this to stoichiometry and different chemical reactions. So we're going to have a lot of uses for this formula. It is on your reference table. You will end up memorizing it because we're going to use it so much, but it's on your reference table so you don't have to memorize it. P is pressure. We'll use ATM, torr, millimeters of mercury, kilopascals for pressure. V is volume. N is moles. R is a constant. On our reference table, we have 3 different values for R. We will use whichever value matches the units that we're using. For example, if our pressure is in atmospheres, then we'll use this first R here, that's 0.08206. If it's in torr or millimeters of mercury, because those two are equivalent to each other, then we will use that third value. We'll use this middle value that's got joules in that later on. We won't really be using that value this particular unit. And then temperature is always in Kelvin. All right, so now we just have an example problem that we're going to work through together. So take a second and read it. One thing that would be helpful here is writing out our equation. So we have calcium carbonate, which is a solid, and that decomposes, so breaks apart to make calcium oxide and carbon dioxide. And we should check to make sure that's balanced, which it is. So we generate carbon dioxide gas, and it's collected in a 250 milliliter flask. The pressure is 1.3 atmospheres, temperature is 31 degrees Celsius, and we are trying to solve for moles of gas that were generated. So we can plug that into PV equals nRT. So P is my pressure. That's going to be 1.3 atmospheres. V is volume. That will be 250 milliliters. But if you look at your constants for R, that's in liters. So that's our clue that we are going to have to change this over to liters. N, moles, that's what we're solving for. R is the gas law constant. So since we have atmospheres, we're going to use the 0.8206. I'm sort of running out of space. And then we need to multiply by temperature, but that's going to have to be in Kelvin. So 31 degrees Celsius. If we add 273 to that to get Kelvin, that would give us 304. I'm going to squeeze that in over here. So now we just do our math. So take out your calculators. All right. Once you plug that all in, we get 0.00130. Let's see how many significant figures we want. We only want 2 significant figures, so we are good with that. So that's how many moles of carbon dioxide gas was generated. Now you can already probably guess how we're going to be using this. If we know how many moles of carbon dioxide gas were generated, we could figure out how many moles of calcium carbonate reacted and how many grams of calcium carbonate reacted. So we'll be doing those calculations tomorrow. All right, so another example. Take a second and read through this and start setting it up. All right, so we are going to be looking for pressure. They gave us a temperature, which we will need to convert to Kelvin. We have volume. Now we have 144 cubic centimeters, which is equivalent to 144 milliliters. Therefore, we would have 0.144 liters. We also have a mass, and from mass we can find moles, so that's the first thing that we should do is convert that over. Since it's N2, we would use 28. That will give us 178. So I'll do 118. All right, now we can start plugging into PV equals nRT. Pressure is what we're looking for. Again, the volume is 0.144. All right, our moles we already found, so we just plug those in. R is our gas law constant, so we are going to use we could actually do either one here since they did not specify what unit pressure is in. We can solve for it in either atmospheres or in torr, so you can use either constant as long as you label your pressure correctly. I'm going to do the atmosphere one. And I'm going to squeeze my units in over here. And then lastly, we got to multiply by our Kelvin temperature, 24 degrees Celsius. If we convert that to Kelvin, that would be 297. So then we do our math. And we get just a little bit under 2 ATM, depending on rounding. So I got from my calculator 1.9947, but I only want two significant figures, so that would end up rounding up to 2.0 ATM. Now, if you had used the other constant and solved for the pressure in torr, that would end up being about 1500 torr. All right, so this is as far as we need to go today. We just need to get comfortable using this formula, and then tomorrow we'll start applying it to more situations. Have a great day.